Hello, everybody. And yes, as for those who stuck to the former version of the program, I am not Nicolas Coltis, and unfortunately, I'm not going to talk about plate tectonics. So I guess it's a rather cheap way to start a presentation like that. But there's a connection between what I'm going to talk about and plate tectonics. You can think of it as we saw in the previous talk by Anne, that it could set the stage to plate tectonics, and also plate tectonics, like outgassing of volatile element and formation of atmosphere, is also a strong manifestation of the coupling that there exists between the surface and the interior of terrestrial planet. And the last reason also is that plate tectonics has also been advanced as a prerequisite for habitability. And so is formation of atmosphere and liquid water at the surface, which is what I'm going to talk about. So this is also the same type of image that we saw this morning. So a lot of this concept have been discussed before. And here again, I want to emphasize that there's a great diversity in our solar system. The Earth, of course, is unique in the sense that it has, as we mentioned, plate tectonics, and it is also the habitable planet with liquid water at the surface. And there's a great variety between this planet in terms of size, in terms of composition, of course, in terms of atmosphere. And so the idea of a comparative planetology is that if we study this diversity, it can teach us a lot of things on our own planet. So that's the motivation behind that. And to illustrate that, this is one of the possible examples that we can look at, which is the divergence between Mars and the Earth, which 4.5 or 4 billion years ago were much more alike, with a dense atmosphere, liquid water at the surface. They are also composed, you don't see it here, but they are composed of silicate and metallic envelopes that are well separated. And they both had active dynamos, and that was a long time ago, but then something happened, and those two planets evolved differently. The Earth is pretty much the same as it was before, so still habitable, still liquid water at the surface, still active dynamos, still plate tectonics. On the other hand, Mars has a thin atmosphere, a dry surface, no active dynamo, and no plate tectonics. So we want to understand, for instance, why and how and when this happened. So I remember this morning, Alessandro showed this slide or this image to show that there was a great diversity in planetary bodies, but I'm going to show that this image to show that there's a lot of similarities between the terrestrial bodies, in the sense that they are all differentiated bodies. So you see they are all composed of a silicate envelope that is surrounding a metallic core. And for me, this is a great indication that earlier on, these terrestrial bodies went to at least one global magma ocean stage, because if you think of planetary bricks as a mixture of iron and silicate, if you want to separate them, you really need to go through subsolidus temperature and even liquidus temperature in order to separate these two materials efficiently via gravitational segregation. So this is the reason why I think, and not only me, that a lot of terrestrial bodies went to at least one global magma ocean stage, which may have lasted for a few thousands of years to a few hundreds of millions of years, depending on the conditions. And in this context, understanding the outgassing efficiency of a volatile element is crucial, because not only because it's the mechanism by which the secondary atmosphere are formed, and also because this atmosphere are going to influence the planetary cooling and evolution, and also eventually planetary habitability. So when we started to look at that with the people, I forgot to mention explicitly their name, of course, but they were in the first slide. When we started to look at that, we realized that there were, people had worked on the coupling between, magma ocean and atmosphere, but the dynamics of outgassing of volatile element had not been studied explicitly. So this is why we started to look at it. And this is also something that has been mentioned in Anne in her presentation. If you think of a magma ocean, this is basically a material with very low viscosity. And so if you express the Rayleigh number, the vigor of convection, with a very low viscosity in particular, then you end up with values of this Rayleigh number that are well above the critical value, 10 to the power 22, 10 to the power 30 for a fully molten magma ocean. Even for a partially molten and even, not even a global magma ocean for the Earth, you would get to values that are on the order of 10 to the power 15, so much greater than 1. So you expect very vigorous convection. And what vigorous convection is going to do is going to cool down the magma ocean very efficiently. And as the magma ocean cools down, it will solidify. So the crystallinity is going to increase with time. So this is what you see in this plot. And this means that as the crystallinity increases, then you also change the viscosity, which starts to increase slowly, but suddenly there's a radiological transition, and you are going towards a behavior that is more dominated by that of the solid more than that of the liquid. And so this means that the magma ocean undergoes different stages, which are summarized in a very crude way here. You start with a completely liquid magma ocean, and then at some point you will start to solidify. So there's many ways you can solidify the magma ocean. Here I just assume, for simplicity, that you start from the bottom, but there are many other possibilities again. So you have this solidification front, you have here a machine mantle and essentially liquid silicate magma ocean that is in contact with the atmosphere. And eventually this solidification front will reach the surface, so you end up with a machine mantle, perhaps with a basal magma ocean, as it has been discussed before. But this is the stage that lasts for the longest, but actually this is not what I'm going to focus on during this presentation. I'm going to talk about the stage where you have essentially liquid or liquid magma ocean as it is in contact with the atmosphere. And so in this context, when the outgassing of volatile element occurs through two processes. The first one is that you need to bring material to the shallow depths, shallow pressure, at which you can start to form bubbles. And this is essentially what happens when you open up a bottle of San Pellegrino or Coca-Cola or beer, anything that contains volatile. And so you decrease the pressure, you form bubbles. The bubbles, they rise to the surface because they are lighter. And so this is the second stage, bubble migration towards the surface. So I'm going to talk, So what is important to notice is that all the studies that have focused on these two stages, they have assumed that they are very fast. So they are very fast. The exsolution, the formation of bubble is very fast in the magma ocean because you have a vigorously convective magma ocean. So you expect to have a lot of convective cycles that are very short. So you should expect to bring all the materials to the shallow depths, and then you expect the bubbles to rise very quickly because they are much lighter than the silicate magma ocean. So today I will not focus on this one. I will focus on this bottleneck. But with these two assumptions, this basically brings us to the assumption that you expect a complete and instantaneous outgassing of volatile element in a planetary magma ocean, and we wanted to test this hypothesis. And so again, this is what I will focus on during the rest of this presentation. And this is the system we want to model. So basically a vigorously convective liquid magma ocean in contact with the atmosphere. So here you have what I mentioned before, this depth or the pressure at which you start to form the bubbles, which I call the exsolution depth or GE in many slides that you will see. And at the bottom, you can imagine that you have a solidification front. So you have a machine mantle. This is equivalent or similar to having a no-slip boundary, and here a free slip or a free surface boundary. So we want to model what is happening in this system. This system can be summarized like that. Basically, this is a system that is heated from below and cooled from above. And we want to determine what's happening inside. For that, we relied, in the first set of experiments that I will show you, we relied on the numerical modeling. So you don't need to look very, very deep into the equation. What is important is that we are solving for three conservation equations, the conservation of mass, the conservation of momentum, which is simply Newton's law applied to a fluid, and also the conservation of energy. And these are written in dimensionless form, so that's why you see appearing two governing parameters that Anne already mentioned in her presentation, thanks to, which is a good thing for me. I don't have to explain this too much in detail. Again, the Rayleigh number is the convective vigor, which we vary systematically from 10 to the 8 to 10 to the 12. And the first set of experiments that I will show you, we kept the Prandtl number to 1. So 1 means that you have really a fluid. So basically momentum, diffusion, and thermal diffusion are equal. And so these are different snapshots that we've obtained from different numerical experiments in 2D or 3D, a different Rayleigh number. So as we go down, the Rayleigh number increases, and you can see for both 2D and 3D that with the Rayleigh number that increases, the structure becomes smaller, the turbulence becomes more important. And we managed to reach to a state where we have a statistical steady state. So it's not purely a steady state, but it oscillates around a mean value for all the quantities that we're interested in. And we prolongated this state for hundreds of transit time. And transit time is something that I will mention a lot during this presentation. It's simply the time it takes for one fluid parcel to travel from one horizontal boundary to the other in one direction or the other. So we prolongated these experiments for 100 transit time. Sorry. So yeah, we have reached relatively high Rayleigh number, but we are far from the 10 to the power 30 that I mentioned at the beginning of my talks. But we still believe that we've reached an appropriate regime for the magma ocean. This is one of the experiments that I showed in the previous slide. So I'm going to show you a movie of it. So this is a temperature field. Red is hot and blue is cold, and what you're seeing is convective motion. So the hot stuff is lighter, so it rises to the surface, and dense material is, and cold material is denser, so it goes down. You have a large-scale circulation, and you have also smaller-scale motion, which is typical of this type of regime we are in. And so this is in this domain we wanted to characterize the efficiency of X solution. Okay, and so basically the efficiency of the material to bring a fluid parcel to shallow depths. And for that, we use what I will call the quantity that I call the D mean, which is the minimum depth that was ever reached by a fluid parcel during its history. So this is summarized here. You have one of these fluid parcels, you follow it, and at some point it will reach the minimum depth. This is what we want to track. We track it everywhere in the model domain. This is initially this minimum depth, so initially it's the distance to the surface, but you will see that with time it's going to decrease because of convective motion are bringing material to the surface to shallow depths, so D mean is bound to decrease with time. And so this illustrates also that it takes some time to absorb the material because it takes some time to bring material towards shallow depths. And so we wanted to be a bit more quantitative about that. So I'm showing you different snapshots in time for similar experiments. So this is the minimum depth. You see that it's decreasing with time. This is the equivalent histogram. So initially it's flat histogram, of course, but with time it will decrease and tends towards this shape. And so what is important also to notice is that even after several tens of transit time, you have some material that hasn't reached the shallow depths. Some of the material has, but not everything. And we wanted to quantify this a bit further. So to quantify this distribution, we tried to quantify the average value of the minimum depth and its standard deviation. So this is the two quantities that I'm plotting here as a function of the dimensionless time for different numerical experiments in 2D and 3D. So you see they are all following the same trend, but they are not exactly the same trend. But now if we do the same, if I represent the same thing, but this time as a function of the transit time, again, the number of time fluid parcel travels from one surface to the other, then you see that everything is collapsing very nicely. And this is a very important result because it shows here, at least, that outgassing efficiency is essentially a function of the magnitude of the convective velocity because this transit time is also directly proportional to the magnitude of the convective velocity here. So that's an important result. With this, I'm not going too much into the detail, but we were able to characterize even better this distribution using the two quantities that I showed before that we can characterize, and we can determine this histogram as they can be described as a normal Laplace distribution. So no need to go into the details, but basically with this we can predict the outgassing efficiency analytically for any time and any Rayleigh number values. So we use this expression to determine the exalt fraction of volatile in the magma ocean of the size of the Earth's mantle. So this is a very high Rayleigh number, still low Prandtl number. And you can see the exalt fraction of volatile for a given exsolution depth. So this is actually a quite high value of the exsolution depth. You would expect much smaller value of the exsolution depth. But even in this case, which is favorable to outgassing, you see that it takes a lot of time, several thousands of years. So it may seem small on a geological time scale, but if you compare this to the lifetime of a magma ocean in a fully liquid stage, it's quite significant. And it's even longer if you consider smaller exsolution depths, which are more reasonable, by the way. Okay, so again, this shows that outgassing in magma ocean is not instantaneous, and that volatile species may remain in the magma ocean for times that are comparable to the lifetime of the magma ocean in a fully liquid stage. So this brings me to the first take-home message. Again, outgassing efficiency depends on the magnitude of the convective velocities. Volatile outgassing in the convective magma ocean is neither instantaneous nor systematically fast, and again, a significant fraction of volatiles can remain in the magma ocean after the end of the fully molten stage. What was not entirely satisfactory with this experiment is that they were conducted at the same Prandtl number, and we know that the Prandtl number should evolve with time. So should the thickness of a magma ocean, as I showed before. The thickness of the magma ocean in a fully liquid state should decrease with time as it's cooling down. So we needed to rely on additional experiments, and with this we relied on joint numerical and analog experiments. So this is the experimental setup. Again, we want to determine in this convective system the efficiency of outgassing as a function of two governing parameters, which are again the Rayleigh number, the convective vigor, and this time the Prandtl number, which is inversely proportional to the inertia. We wanted to determine this as a function in terms of flux of exalt volatile, in terms of scaling laws that we can extrapolate to planetary conditions. So for that, as we've seen before, we can do it with numerical experiments, which allow us to determine the fluid motion. And with the fluid motion, we can determine the exalt fraction of volatile with time. We can also determine this, the fluid motion in a different way. What you see here hasn't been computed, but it has been measured in a very nice analog experiment, which is actually unique in our community, which we set up thanks to Angela, who must be around here, I think, among us. Yeah, I saw her. And so this allows us to do exactly the same treatment as a numerical experiment, and therefore to cross-validate the numerical and the analog experiment, which is something that is rarely done in geodynamic studies. So a little bit more about this nice experiment. So this is a particle tracking velocity method. So this is a close-up view of the experiments that I showed earlier. So you see here a tank which contains a fluid which is heated from below and cooled from above using thermostated bath. This tank is also illuminated by a powerful LED light, and it also there's also 4 cameras that are at different angles, which gives us information about the depth. And inside this tank, we see the fluid with plastic beads, which are very small and almost neutrally buoyant. And with those cameras, we can track them. And by tracking them, so this is another view. So this is a close-up view of this area. So you see those particles. And this is the track that we can reconstruct with the cameras. And with the track and the information of the track evolution with time, we can reconstruct the 3D velocity field everywhere in the model domain. Actually, this is even the 4D field because there's also the information of time. Yeah, so that's what we can do with these experiments. And so we compare the analog and the numerical experiments, and we found a good agreement between the two, which again cross-validate the approach. And we also find a good agreement between our numerical and analog experiments and results from the literature, as you can see here. So this is all satisfactory. And we moved on further to try to characterize the outgassing efficiency with this type of experiments. So what you see here is the Exol fraction of volatile, again, as a function of the number of transit time, for different value of the exolution depth. So this is coming to a result that I already mentioned. The larger, the deeper the exolution depth, the easier it is to exsolve the volatiles, and vice versa. And with this, we were able to describe semi-empirically the flux of exolved volatile, which again is a function of the magnitude of the convective velocity, of the exolution depth, and also of what we call the exolution factor, which in our experiments seem to reach some sort of asymptotic value. In fact, if we prolongate this, we could even, I could argue that we can go to either larger or smaller value, but in what I'm going to show you next, I would argue that there are lines of evidence for which we can argue that this can either remain constant or even decrease depending on the complexity that we consider. So here we've considered that it is constant. After, it's asymptotic behavior. And we use this expression to, this time, to evaluate the couple magma ocean atmosphere evolution. So for that, we relied on standard parameterized convection models that have been used for this type of studies. So basically, these models, they rely on thermal evolution. So this is a heat balance equation. So the temperature at the top of the magma ocean is going to decrease or cool down as a function of the convective heat flux. This convective heat flux is directly proportional to the Rayleigh number that I mentioned earlier, and also to the temperature difference between the surface and the top of the magma ocean. This convective heat flux is balanced by the atmospheric heat flux, which here we assume that is radiative, but in other cases we can also consider a convecting atmosphere. And we close the system, because we need to close the system because this atmospheric flux depends on the opacities, which depends on the chemical species that are present in the atmosphere, which vary with time. And so we need to close the system by making a mass balance that basically describes how volatile elements are going to partition between the atmosphere, the magma ocean, and the solids that are progressively formed. So usually these models, they assume equilibrium outgassing, in which case you can describe the amount of volatile present in the atmosphere with this simple expression, but we relax this assumption to make it more general using this expression, which directly derive from the expression that I showed you in the previous slide for the flux of volatile outgassing. And so I'm going to walk you to a typical Earth-like example where we've considered two greenhouse gases, which are CO2 and H2O. And what you will see here is the CO2 pressure, which is basically the amount of CO2 that is present in the atmosphere as a function of time. The dotted line in all the plots that I will show you represents the equilibrium case. Basically, equilibrium case means the case where everything is outgassed instantaneously into the atmosphere. This is the standard assumption. And here, in continuous lines, it's our assumption of delayed outgassing. You see that immediately for the equilibrium case, you form an atmosphere, but in reality, it takes some time to form it, several tens of thousands of years. And if you do the same thing for H2O, you get the same result, but it's even more pronounced. This effect of this delayed effect is even more pronounced because H2O is even more soluble in water, meaning that the exolution depth is going to be smaller. So it's harder to exsolve H2O. And what you see is that after a while, they all reach these models reach the value of the equilibrium models. So you outgas everything once you have solidified your magma ocean, which is what you expect. But in the meantime, the evolution is different because since you don't have an atmosphere at the beginning, it takes some time to form it. You don't have a greenhouse effect during this period. Greenhouse effect is going to increase because you start to release greenhouse gas into the atmosphere. So this decreases the emissivity. And so at some point you start to have a more important greenhouse effect. And this means that without important greenhouse effect at the beginning, you are going to cool down the magma ocean much more rapidly than in the equilibrium case. And this is what we see here. Dotted line again are the equilibrium case. You see it takes longer to cool down the surface and temperature and the temperature at the top of the magma ocean than for the case where we have a non-equilibrium outgassing. So to summarize, out of equilibrium outgassing, or exsolution I should say, delays outgassing, reduces greenhouse effect, and accelerates magma ocean cooling and solidification. So we try to quantify that a bit more systematically as a function of a planetary mass, and this is what you can see in this plot. This is the ratio of the time it takes to solidify the magma ocean. This is the ratio of the two times, the solidification time at equilibrium, the solidification in the case where you don't have equilibrium outgassing, and you can see that in the case in particular for large planets, so you can actually have a solidification time that is 30 times faster than the equilibrium case, which is not nothing. So it certainly has an important, significant effect. Then we wanted to investigate further whether the out of equilibrium outgassing or non-instantaneous outgassing could affect the other, could result in different storage of volatile element, because some observation on Earth suggests that you have some antigas reservoir, in particular for helium-3 elements. And so we investigate that in the frame of what people call the basal magma ocean scenario that was proposed almost 20 years ago by Labros and collaborator, which has been recently confirmed by more elaborated simulation. But in this simple frame, which is a bit certainly much more simplified than here, basically this is the way it works. You have a global magma ocean that you start to solidify somewhere in the middle, not in the bottom, not from the bottom. And this means that you're going to separate the surface magma ocean from the bottom magma ocean. And some part of it can host some volatile, for instance. So we wanted to investigate how much of the volatile we could store in this basal magma ocean. And we've investigated here with this couple parameterized convection models. So what you see here is the partitioning of helium-3. Again, this is a rare gas that for which observations suggest that there's an antigas reservoir in the mantle at the present day. And this is the partitioning of this helium relative to the initial value. So initially, this is time. Initially, everything is in the magma ocean. And with time, you are going to release helium-3 into the atmosphere. This is what you see in blue. At some point, the magma ocean is cold enough to start to solidify somewhere in the middle. So you form this basal magma ocean. And you can store about 10% of the initial helium-3 in this basal magma ocean. And this is a lot, because if you were to do the same exercise for a case where you have equilibrium or instantaneous outgassing, you would basically store nothing. Okay, so this shows that out of equilibrium outgassing can create and preserve antigas mantle reservoir in a way that you could not if you don't consider out of equilibrium outgassing. Something that we are currently working on, so we have added the possibility of having a radiative convective atmosphere thanks to Emmanuel Marc. So this is the work of Alessandro who is our PhD student. And he produced this map, which you can call the habitability map. So here the criteria that we use for habitability is the ability to maintain liquid water at the surface. And this is these maps, so this corresponds to this blue area. This is where you can condensate water at the surface. And this is as a function of the initial water content and as a distance to the sun. So this is the area where you might expect potentially, life to be compatible. Okay, this is for the case where you have a equilibrium outgassing, instantaneous outgassing again. Now you do the same thing for everything being equal, except for the case that it's non-instantaneous outgassing, and you see that this area, this habitable area, let's say, has been enlarged because basically, as we've seen before, non-equilibrium outgassing, they can drive the temperature to colder states, which are more favorable to condensation of water at the surface. So this shows that even these are preliminary results, that out of equilibrium outgassing can contribute to planetary habitability. So these are the conclusions. So I already mentioned this point several times, so I just want to focus on the last one. So this basically out of equilibrium outgassing has a strong influence on planetary evolution. It leads to faster cooling. It favors the preservation of undergas reservoir. It impacts water condensation and hence habitability. Just very quickly, what we're currently working on is adding more complexities to this scenario. So this is also the work of Alessandro is to consider rotation, which may be important in Magma motion. This is the case that I showed earlier without rotation. This is the case with rotation. You can see that the structure is very different. And you expect a very different efficiency of outgassing. This is what we see here. This is the case without rotation. Exalt fraction is here. With the case with rotation, it takes much longer time to exsolve, much more than what we were expecting. So this is something that we are investigating further. Another complexity before I finish is to account for the effect of variable viscosity. This is similar to also what Anne has presented actually. So this time we consider that the viscosity is temperature dependent, could also be depending on the amount of volatile. And you see here, this time this is a movie of the viscosity. So red is viscous and blue is not very viscous. So you're forming sort of micro plates. There's also a yield stress that is considered here. And this also impedes the outgassing. You can see here, even after 160 transit time, you haven't exsolved, slightly more than 80% of the volatile for a relatively large exsolution depth. So this is something that we want to investigate further, and I'm going to stop on that. This is also other complexities that we are trying to investigate, that we plan to investigate in the future, where we have interaction of crystals and the silicate magma ocean. And I guess I'll stop here before you get mad. Thank you.